when we differentiate a function, we get the, what did we just get when we were differentiating?
Gradient.
The gradient function. It describes what is happening to that graph. It is describing the rate of change, all right? The rate being a number, we just call it increasing, decreasing, zeros, all those sort of things. But that picturesque model of increasing and decreasing, the maximums and minimums, can be applied to anything that has a formula. So if we've got a formula, when we differentiate, what we get is the rate that whatever that formula is talking about is changing. So let's have an example. It's pouring with rain and rain's coming down a spout and there's a puddle on the ground and that puddle is growing, all right? We can say that that puddle has a particular formula for its area. The rate that area is changing will be found by differentiating our area formula. That will give us the rate the area is changing. So when we were doing optimization, we had the rate at which the area of the field was changing. We were only interested in its maximum or minimum. So we made that rate of change equal to 0 to find the maximum or the minimum value. What we're going to look at today is just finding a derivative, a first derivative, to find out what the rate of the change for any equation is, and substituting into it to either find that particular value, that particular rate of change at a certain point, or we might be trying to find the maximum or minimum. All right, so the first derivative this is usually only an achieved, or if it's a little bit more technical one, could be a merit question. But basically all you're doing is you are taking that value and differentiating it and finding out what the rate of change is. Grab an example. What's the area of a circle's formula? Nice going. The area of a circle with the formula of pi r squared. We want to calculate the rate of change All right, so it will always tell you what the actual rate of change is changing with. So in this particular case, we've got r in our formula. So it's changing with respect to the radius. So what is the area of the circle? No. What is the rate of change of the area? When r equals 2 centimeters. All right, so it'll be something quite simple like that. You actually don't even need to understand that, to be honest. It would be good if you do. But what we're saying is that that area of a circle changes depending on what the radius is. So if the radius is slowly changing, for instance, that example of the water dripping into a puddle, circular puddle, it's slowly getting bigger. If we can find out the rate at which it's changing, then we can answer the question about when its radius is this, how much is the area? You want to say that the radius, that the area, it's hard to see, isn't it? The area. You want to say the area is going to be 2 squared is 4 times pi. That is the area of the circle, but it's not the rate with which it's changing over the increasing or decreasing of r. Okay, so what we have to do is differentiate. Now we get that a bit of a different notation. Because this is y, it goes on the top. This is the x in our equation, it goes on the bottom. So the a by the r, and you'll remember I said that this particular notation is quite helpful, means that we are differentiating this. What will we get? Good. What's that the formula for? Circumference. Good. That's got absolutely nothing to do with it though. All right. It just happens that the rate of change of a circle is equal to the circumference formula. But we want to know what that is at r equals 2. So dA by dr, the rate at which it changes is equal to 4 pi. Happens again to be the same amount. But centimetres squared. That means that at that particular time, it is changing by 12 centimetres squared. The area is changing per centimetre by 12 centimetres squared. So it's getting 12 centimetres bigger at that exact moment. And if we went to another point, let's say at r equals 3, so if we were looking at the area, it would be 9 pi. 3 squared is 9. But the rate at which it's changing is equal to 6 pi. All right, 3 times 2 times pi. So it's not the same thing. It's changing by that much as far as the radius is concerned. So very simply, we're differentiating whatever the thing is that we're interested in to get the rate at which it's changing and substituting in values.